All right, hi everyone. This is your warm-up. This should be in your note guides for lesson 3.6. So I'm going to recommend you go ahead and pause the video until you've actually completed this warm-up. Give yourself a chance to give this problem a go, and I will work through our solution in, let's say, a countdown of 3. So pause the video. 3, 2, 1. Okay, so I'm going to go ahead and jump through this. Our two angles that we have measures for in our diagram are classified as alternate interior angles. Now we're asked to find x so that these two segments are parallel. Therefore, our alternate interior angles, we want them to be congruent. So we're going to go ahead and set them to be congruent. So I'm going to go ahead and write that their measures are equal. 9x minus 21 equals 7x minus 3. And from here, we'll simply solve this equation for x. So I will go ahead and move some things around so that what we get 7x equals 18, 7x, sorry, 2x equals 18, and x equals 9 will be our answer. Okay, so moving right forward, today we're going to be talking about, the topic is perpendiculars and distance, but overall how to find the distance between a line and a point, and then in a separate video we'll cover finding the distance between two parallel lines. So to begin, this is kind of our overarching task, let's say, for this whole lesson. How do we figure out the distance between this point Z and this line A? So I ask this question at the beginning without necessarily telling you how, because I like you to, think about it. A lot of times I see students say, well, let's just count like down along my grid lines how many spaces away, for example, Z is from the line. So we could do that, perhaps. You might go the other direction, though, right? We could go to the line from point Z along our horizontal grid lines. And does that come out to the same answer? I think it does in this case, but I'm not sure it always would. Now you might imagine, like, I could draw a line like here and try to figure out what that length is, and here and what that length is. Ultimately, this is hopefully showing somewhat of a problem. We have maybe all of these different ways of finding distances that aren't all the same number, aren't all the same answer. So we want to narrow in on what are we actually going to define as the distance. So here we have a definition, the distance between a point and a line. So the distance between a line and some point not on that line is the length of the segment perpendicular to the line through the given point. So there is going to be only one of these. I'm going to sort of underline or sort of shade in this particular line here. We see all these different options connecting that point C to this line AB, and only one of those is actually perpendicular to the line AB. And that's going to be the one we care about. Now I'm just going to make a note here. Distance, this is something to know beyond just today. Distance is always measured perpendicularly. Length, distance, always measured perpendicularly between objects. So maybe I'll phrase it as always measured along a perpendicular line. Along a, here's our symbol for perpendicular line, and I'll put in parentheses, between objects. So between points, there's not really a way to say that those are perpendicular if it's just points, but between any other geometric objects, we're going to be looking for that perpendicular distance. Okay, now this is our perpendicular postulate to basically justify, if I were to flip back here, the perpendicular distance is the only distance there. Let me clarify that. The perpendicular line that represents the distance we're interested in, there is only one of these. So our perpendicular postulate says if we have a line and some point that's not on the line, then there is only one line through that point that will be perpendicular to the other one. And we covered what was called our parallel postulate last week, and this is almost the exact phrasing, except this time talking about a line being perpendicular. So here it's helping to justify that there is this consistency. If we find the perpendicular distance, it's the only one like it. So we can see that at play with this kite. We have a kite here, and the, let's say, like crossbars of our kite. And the question that we're asked with this figure is, which of these segments represents the shortest distance from A to DB? And I'll go ahead and let's call out DB. DB is this crossbar. Okay, so the key here is we're looking for the shortest distance, therefore it will be the perpendicular distance. AB is not our answer. AD is not our answer. It's A to, it looks like X is the point there at the intersection of the crossbars. So AX is definitely going to be the shortest distance as it is perpendicular. And again, I'll just use my perpendicular symbol. Okay. So all in all, we want to focus on, again, this task of trying to figure out the distance between a line and some point that's not on the line. So I have this slide, and you have a section in your notes to sort of brainstorm, like what kind of information do we need? You can sort of sketch to yourself, like where would this perpendicular distance perhaps be? And that might give you a sense of like, okay, what information do I need to know to figure out how long that particular distance is? And let's think about, well, do I know like the slope? Do I know anything about A? Maybe I need the equation for A, like y equals mx plus b, something about A. I need to know where z is, like where does that point in space actually live? And then we can really focus in on, okay, so what is this segment? What line maybe is that segment on? Where does it intersect A? Let's dive into kind of outlining these steps here. So here's an actual example that we're going to be working through to illustrate this task. So we have line S, and line S here, we have 2 points on line S, looks like 1 point at -5,5 and 1 point at 0, 0. And then we have this point V that's not on the line, and V has coordinates 1, 5. So we want to figure out the distance between line S and point V. So overall, we are looking to find this perpendicular distance. Okay, now we know that this perpendicular segment that represents the distance here is along this line that is perpendicular to line S and goes through our point V. So we need some information about that particular perpendicular line, and I need to know that point where the perpendicular line and my original line S, where those two intersect. So we kind of have some overall steps to think through here. First of all, we need the equation of the original line, S. We also need the equation of that perpendicular line that goes through the other point V. I need to know where exactly the two lines intersect, because if I know point V already, it has coordinates 1, 5, and then I figure out that intersection point, then I can use perhaps my distance formula to figure out how far apart that intersection point and point V actually is. So that's the overall task, right? We're going to go ahead and walk through this example though. So part 1, figuring out the equation. So we have 2 points. I'm going to aim to have us write this equation in slope-intercept form. I also just want to note This is an example where I'm not given the equation. I actually have to find the equation by figuring out the slope and figuring out the y-intercept, etc. But you might imagine another example, you might be given the equation, so you can kind of skip this step. Here we have a little bit of work to do. So I'm going to start by figuring out the slope. So we'll use our slope formula, the rise over the run. So we might take our y-coordinate of 5 and subtract 0. Our run, take our x-coordinate of -5 and subtract 0. So really, that's just 5 over -5 or -1, which you might have also been able to tell just by looking at the graph, which also works. Now, we could go through the algebraic process of figuring out our y-intercept. Remember, to do that, take your slope-intercept form, plug in your slope. We just found m, which is -1. Plug in your x and y coordinates from one of your points. So you could plug in, for example, like 5 and -5 for y and for x, and of course -1 there for the slope, and then solve that equation for b. B would be the only thing we don't know if we plug those other values in. We can do that, except we also have the graph here. Not every example is going to give you a graph, but we have one, and we could see pretty clearly that, oh, the y-intercept is just 0. So that's actually nice and simple for us. Our equation when the y-intercept is 0, meaning b is 0, it's just going to look like y equals mx, or -1x, or really, we can just keep that even simpler, -x. That is the equation in this example of the original line S. Okay, so we have that. What else do we need? Well, we need the equation of this perpendicular line. I'm just going to go forward calling this line T. So we have S and T. And this line T has two kind of characteristics. It needs to be perpendicular to S, and it needs to go through my point V. So let's remember what the equation for S was. I'm going to write this up in the top right corner. Y equals, maybe I'll keep it as -1, -1x. I write the -1 just so we can remember the slope was -1. So if my equation of t is going to represent this perpendicular line, the new slope needs to be the opposite reciprocal of -1. Okay, so the opposite reciprocal of -1, let's pretend -1 is written as a fraction. -1/1. Well, what happens when you turn 1/1 on its side? It's still 1/1. The opposite part means, of course, it's going to be positive. So our slope actually this time is just +1. Now our y-intercept, we can see the y-intercept on our graph again when the slope is 1. It does sort of make things nice and easy. We can see the y-intercept. You won't always be able to see the y-intercept, so just as a reminder, when you need to solve for that algebraically, what do? We plug in our coordinates. So the x and the y, this time we're looking at point V's coordinates. So we'll plug in 5 for y. The slope we said was 1, but the x value is also 1 from that point V. So if we solve for b using this equation, we have 5 equals 1 plus b. Subtracting 1 from both sides, we can see from the graph and solve for algebraically the y-intercept of 4. So putting our slope and y-intercept together, the equation of this perpendicular line t is y equals 1x, or just x, plus 4. Okay, so the next task is to figure out exactly where our two lines intersect, and we're going to call this point I for intersection. So I'm going to remind us at the top here, S had this equation of just y equals -x, and t had the equation y equals x plus 4. So I basically need to figure out where do these two lines intersect. Again, with this particular example, it looks pretty clear from the graph where they intersect. Looks like the x-coordinate would be -2 and the y-coordinate would be +2. Now, in circumstances where the graph shows it really clearly, go with it, run with it. But it's not always going to be the case, as you might understand. So I'm just going to make sure that we have an algebraic understanding of how to do this too. So I'm going to go ahead and solve this system of equations. My two equations, y equals -x and y equals x plus 4. There are generally two ways of solving a system of equations: substitution and elimination. And you can use whichever you prefer. But just as a reminder, substitution looks like plugging in an expression for one of our variables. For example, both of our equations are set equal to y, right? Y equals something and y equals something else. So I could plug in one thing that I know y is equal to for y in the other equation, meaning I can like set these equal to each other, right? -x equals x plus 4. And I can solve for x using that equation. Now, the other option is elimination, and we might not have done that maybe as often. So elimination tends to work by simply like adding, or really adding our equations together when we have variables, like we happen to in this case, that are have opposite coefficients. Like on x here, we have one that's a -x and one that's a +x. So you might have like a -2x and a +2x. Those variables, when we add the equations together, eliminate, hence the name elimination. So I'm just going to go forward with elimination as our first step here. I'm going to add, notice our equations are set up so the variables and everything are kind of stacked together, like our equation sign and everything. So I'm going to add y plus y to get 2y. When we add -x plus x, that variable eliminates, it cancels out. So it's gone. We still have, though, 4, or 0 plus 4. Remember, there was a 0 y-intercept in that first equation. And 0 plus 4 is 4. Carry down our equal sign. And the resulting equation, as it should be with elimination, has just the one variable that now we can solve for. So I'm going to go ahead and divide by 2 to confirm that the y coordinate of point I is 2. Okay, we can then plug that back in, plug y in to either of our equations in order to figure out the x coordinate. We need both the x and the y. So if we say y equals -x, well, 2 equals -x, meaning if I were to, let's say, multiply both sides by 2, x is actually equal to -2. Or you could have gone the other way. Y equals x plus 4, or 2 equals x plus 4, subtracting 4 from both sides still shows that x is -2. So I, this point I, has the coordinates 2, -2. All right. Next up, what do we still have to do? Well, we're ready to find the actual distance. The distance between I, remember, was just -2, let's throw in our negative sign there, and V, which we started out knowing was at 1, 5. So I need to figure out the distance there. You have the distance formula. If you think about that more as the Pythagorean theorem, that also works. I might kind of sketch out that Pythagorean theorem example, so showing my vertical distance and my horizontal distance, the two components there. So my horizontal distance, we might think about like -2 minus 1, but of course we're going to take the absolute value of that. So that's the absolute value of -3 or +3. We have our vertical distance, which we could say is 2 minus 5, but again, the absolute value of that, so 3 as well. Of course, we could see this on the graph. Again, not every question is going to be quite so nicely graphed, so good to have a algebraic background as well. So ultimately, we're trying to solve for the distance, which is this diagonal here. So we might set up 3 squared plus 3 squared equals c squared, x squared, whatever you want to call it, or 9 plus 9, or 18. And we're going to go ahead and leave our answer in simplified radical form. The square root of 18 is not simplified. We would break this apart perhaps as the square root of 9 times the square root of 2, or 3 times the square root of 2. So this 3 root 2 represents the distance between point V and point S. Okay, thank you.